Sí. Bueno, pues vamos a ver familia. ¿No hay nadie de fuera? ¿No va a haber un castellano? ¿Puedes ver que está conectado? Porque si se conectaba gente de SKB, dijo Paolo.
Yo le dije, lo que pasa es que hoy es fiesta en Suecia,
Entonces nada.
Bueno, como se graba, igual sí, eso podría.
Sí, por eso es que...
Pues lo hago en inglés, quizás.
Sí. En inglés y...
En catalán.
Sí, no puedo hacerlo en varios idiomas. No.
Entonces, podemos empezar, ¿vale? Si no dices nada.
Lo está grabando ya, ¿no? Sí, está bien.
A ver si... Es que...
La llamo. Está grabando, sí.
Pero que... A ver. Va bien. Se ve bien.
¿Se ve bien y se oye? ¿Se oye también?
Bueno, había visto una serie y lo hackearon. Estaba Jesús, me parece que estaba...
Pues sí, en México.
Lo hackearon, no sé de
Ok.
Pues empezamos el seminario, ¿vale? Con persuasion sobre difusión en Grimsel.
Y advección. Ok, sí, voy a hablar en inglés, porque ya alguien se lo mira. Okay, so this is the title of the talk, Grimsel Test Site, Long-Term Diffusion. That's the Gts-Ltd project, the LTD project in Grimsel, and this is about radionuclide transfer experiments in Granite. I'll show experiment just with the rock matrix, no fractures, and an experiment with fractures. My co-authors from IDAEA, Debbie, Juan Hidalgo, Martin and Lourdes from the UPC, and then Bill Lanyon, Andrew Martin, and Martin Hoyland. Okay, so Grimsel Test Site, just a small introduction. This is an underground rock laboratory up in the central Swiss Alps. That's an aerial view of the area, and you see a drawing showing the trace of the galleries inside the granite. Right. So this is the partners of the organizations that are paying actually are the radioactive waste agencies from Japan, the Czech Republic, Switzerland, and Germany. And this LTD project is about matrix diffusion in general. Matrix diffusion is when you have water flowing through fractures and it has solutes in solution, maybe radionuclides, whatever, and then these solids can also access the rock matrix by diffusion. So we are studying this process. Because this matrix diffusion, together with sorption, are the main radionuclide retention mechanism in fractured crystalline rocks, which is relevant for repositories for radioactive waste. So this is an in situ, in principle, designed as an in situ diffusion experiment. Later, we see that advection is important as well. But so we have this so-called monopole 2 experiment, because previously there had been a monopole 1, and run between 2014 and 2017. And basically, this is this illustration. We have the galleries of a tunnel inside the Grimsel Test Site, and then we have a borehole with an open interval. And then in this open interval, they're circulating a solution. The solution is Grimsel groundwater, but it contains traces radionuclides. And these radionuclides diffuse into the rock, in principle, by diffusion. We have another parallel borehole, just a few centimeters away, which is an observation borehole. So the idea was to be able to see the arrival of the conservative traces, basically the tritium and the chloride. So just a few photographs. So this is how it looked in the gallery. So you have the two boreholes. You see that they are very close together. So only from center to center is 18.5 centimeters. So these two boreholes going down. One is the injection, the other one the observation. And this is an illustration showing the setup. And this is, it's good to remember this in the experiment. So here on upper right, you see the galleries, and then a whole bunch of boreholes. Initially, during the experiment, we only had two boreholes. So if you look in this figure in the lower part, so the one that has a a blue interval and the one that has the red interval. The one with the red interval is the injection, so that's where we circulate the solution with radionuclides. And the one with the blue interval is the observation borehole. So during the experiment, we only have these two boreholes. After the end of the experiment, so after 3.5 years, there's a whole bunch of other boreholes that were drilled just to collect rock samples. And just to take rock samples to be able to measure those tracers in the rock afterwards. There are several of them, but maybe remember that this 17.001, it's kind of above the injection, interval injection borehole, so closer to the gallery, let's say. But there are several of them. So this is an illustration. This is these additional boreholes that were drilled after the experiment. And here we have actually two of these experiments that were coming at an angle. These two boreholes that were coming at an angle, and they intersected the injection and the observation borehole. So basically, you see the two cores that actually intersect. I find this quite impressive, just because you are drilling more than 10 meters away, and you're intersecting these two boreholes that are 5.6 centimeters in diameter. I think it's quite impressive. I don't know how they do it. Because I mean, you have to really hit them. I mean, it's not. I think it's not so easy, but they do it. So they know how to do it.
So what is this brownish color there?
This is resin, because they fill the intervals with resin before getting equipment out and doing the other work. So that's, you still see some of the resin here. Right. So the rock samples were analyzed for the different traces, which are tritium, chloride 36, sodium 22, barium 133, and cesium 134, and they were analyzed at three different samples, analyzed at three different laboratories in Finland, in Japan, and in the Czech Republic. And then first I'm going to show the 3D distribution of tritium and chloride. So these are the conservative traces, the ones that do not sort, because then you see this preferential transport caused by advection. These you don't see in the sorbing trace, then you don't see this preferential transport distances. All measurements, I mean, I want to qualify all measurements, both in the rock and in the water from the two boreholes, are corrected for radioactive decay back to the start of the experiment. So you don't have to include decay explicitly in the calculation. You just use the activities at T0, just corrected to T0. Right, so this is what I was saying about showing the distribution of these are concentrations in the rock. There's a few samples, and these are all projected on the XY plane. XY plane is the plane perpendicular to the injection borehole, let's say. So here 10,001 is the injection borehole, and 12,001 is the observation borehole, and then we have these other boreholes that are the ones that were used for getting rock samples. So you see that if transport were purely by diffusion, then you would expect to see, circular contours. I mean, rather with the center in the injection borehole. Actually, this is an interpolation, but what you see is that you have a preferential transport direction towards the 17,001. That, if you remember, so 17,001 is kind of above the injection interval, so going to the gallery basically. And this is the same for chloride 36. Again, you see this preferential transport, so you see increased concentrations going in this general direction of 17,001, so going more or less towards the gallery. And here I have these plots we have activities of tritium and chloride 36 in the program of rock versus Z. So Z is the coordinate parallel to the borehole. Increasing Z means going down into the rock, and negative Z is going to the gallery, basically. So you see that actually you have the higher activities when you go to the gallery. So you have preferential transport distance going to the gallery. So here you see how it's not just diffusion in the rock matrix, but you actually do have advection in the rock matrix and in the pores of the granite. This is a sort of a 3D distribution plot that was made by Bill Langen, and then you see basically the different borehole, the injection, the observation borehole, and then the different boreholes that were used to get the rock samples, and then color-coded the measured activities for tritium and for chloride 36. The color scale is the activities, and it goes from blue, low activities, to red, high activities. So you have in general, higher activities as you move closer to the gallery. This is a logarithmic scale, by the way. So you see these increasing activities as you move closer to the gallery. So then it's clear that we need to take advection into account. So again, higher activities towards 17001 or negative Z. So you have this flow, this preferential transport in the general direction of the tunnel. Before we had these rock samples, I mean, the experiment lasted 3.5 years. So during the experiment, we have data from the injection and the observation boreholes, the evolution of the activities in the waters of the two boreholes. And we did some modeling using those data. But these initial models were basically just 2D, so we considered the plane perpendicular to the borehole. Right? So you have basically here, this is for tritium, so relative concentration versus time and logarithmic scale. And these points up here in black are the evolution of the concentrations in the injection borehole, and these empty points are the evolution of activities in the observation borehole. These are different model curves. The one with pure diffusion, which is this dashed line, kind of underestimated the drops, so we had higher activities, but if we include advection, which is now only in this XY plane, we could capture the evolution. So we say, okay, I mean, the evolution of activities in the injection borehole is consistent with having some advection across the borehole. However, for the observation borehole, we always have a large overestimation.
Sorry, but how do you include the advection in this?
Advection is about, here you see the tracer tool. So basically you define your gradient, and then you have an homogeneous permeability, and then in this case, this flow goes in this direction. So at an angle between the two boreholes, but here the flow is in this XY plane, so it's in the plane perpendicular to the boreholes. That's why we are not capturing the observation borehole, because here's the same. This is for chloride, it's the same story basically. But what happens if I go back is that, of course, I mean, we saw afterwards, after the end of the experiment, after measuring the activities in the rock samples, that the preferential transport direction is not in this plane, so it's actually perpendicular, more or less, to this plane. So if you include advection, the evolution of the injection interval, it doesn't depend so much on the direction of advection. You just have water across the borehole and takes activity away, so that we can capture that. But the observation borehole, if you don't get the direction right, you'll never be able to model that. That's why, because actually the flow is going kind of perpendicular to this. So, conclusion, I need a 3D model. Okay, so that's what we did. And this is the concept behind this 3D model. So we have here this illustration, we have the tunnel, the gallery, the two boreholes, and basically what we have in this, we have here some lamprifier guides and some small fractures, but at depth, we have a transmissive fracture, and closer to the gallery, we have this particular lamprifier, which is also transmissive. They have high transmissivity, so you have these two permeable features that actually fix the hydraulic heads. So you have a hydraulic head fixed at depth here, and down the borehole, let's say, and a hydraulic depth closer to the gallery, fixed by this lamprifier here. So actually, we have a local here in this region. So this I3, these green intervals, is the injection interval in the injection borehole. So in this region, locally, we have this overall gradient between here and here, which is about 3 meters per meter of gradient. So conceptually, we have our model domain, so it's kind of this shoebox, and you have, the Z direction is parallel to the two boreholes. So you have the injection borehole, the interval in red, the blue borehole, we have the backers and everything as well. And for the modeling of flow and transport, we use transdense, and basically what we did, since we know the hydraulic heads, basically this would be the fracture at depth, and this would be the lamprifier closer to the gallery with these fixed hydraulic heads, and we have about 30-meter head difference in 10 meters of rock, so it's about 3 meters per meter. So with this overall gradient, then we calculate flow, which is flow at steady state, just given by this overall gradient. Flow, and then we have solid transport, which is basically given by an advection dispersion equation.
Do you have density coupling? Because if
No, we don't have, I mean, we use transdense, but we could have done transient.
Okay.
Transdense.
Yeah.
But for some practical reason, because transdense accepted a larger mesh, more elements, than we use transdense, but we don't use any.
that makes sense.
It's not, it's constant density.
I didn't imagine you needed it here.
We don't need it, but for practical reasons, we needed it just because we use a larger read for transdense.
Gotcha.
That's the only reason. So again, that's the conceptual model, and that's basically how we implemented that in the. So we have this kind of shoebox and the two boreholes and the different intervals. Right. Let's start with tritium, which was the first case. I should mention that all this work for this was basically done by David, his master thesis for tritium, and then he continued after that with the other traces. So the number crunching was done by him. Yeah. So this is basically the 2D section of the mesh. So basically, you see the section is 4 by 4 meters. So in the central area, we have a much finer mesh. That's where we have the two boreholes, injection in the observation borehole. And then what then we did, basically we ran a whole bunch of cases. So we did a sensitivity analysis, which at the end we got our base case, which basically is our best fit, which is with these values of conductivity, porosity, diffusion coefficients, flow direction, and the measurement. We check sensitivity with respect to the conductivities, porosities, diffusion coefficients, also two variants of the flow direction, slightly different, and also different meshes. So at the end, our best case is this one, and this is one, then this is the one we use when calculating the other.
Sorry, is
Yeah.
any measurement of permeability?
Yeah. So this number is 10 to the minus 11 meters per second, and it's right in the range measured. So probabilities at Grimsel are about 10 to the minus 11. So it's an unfractured granite, but it's more conductive than your typical crystalline rock in Finland or Sweden. Well, I mean, it's up in the mountain. It's not really confined at depth, but you're up in the mountain. So even it's impermeable, but not so extremely impermeable. So conductivity is 10 to the minus 11. It's low, but not super low.
10 to the minus 11
meters per second.
That is meters per second.
Yeah, here is in meters, yeah. Because in transdense they use this meters per day, but I think in meters per second.
All the other cases, they're different cases or they're different?
Yeah, so it's 0.2 this value, this number means so 20% this value, 60% this value, 80% this value, etc. So higher and lower, we checked higher and lower values.
But you have the same permeability everywhere. You don't have any layers or any.
It's homogeneous, yeah. The model is perfectly homogeneous, except the intervals themselves. They have larger permeability, and the markers they have small permeability. But the rock is perfect. The model is perfectly homogeneous. Yes. Yes.
I missed the beginning. Was the geology pretty homogeneous as well, or is it just an approximation?
I mean, overall it is, yeah. In detail, in some details, we should see.
It is very small scale.
Yeah, it's also we are talking about 4 meters per 4 meters per 10 meters.
That's huge scale for me.
You have some very small scale permeability, small scale heterogeneity. I'll be discussing that, but the model is relatively simple. I mean,
just to understand.
the rock is homogeneous. Yes.
Sure.
Yes.
Where?
So basically, with this base case, which is again this conductivity of 10 to the minus 11, and then we got this fit with the effective diffusion coefficient for tritium. Tritium is the same as water. It's water with one of the hydrogen is tritium. 3.3 10 to the minus 12, and porosity, but this is an important number, 0.0014. Now discuss it. But basically, this is the fit. These are the points are the measurements in the injection borehole, so going down with time. And these are, here we have the concentrations in the observation borehole. Well, we capture them pretty well. It's not perfect, but then the model is also simple. But we can capture those rather well.
Sorry, do you mind if I interrupt?
No.
Is this effective diffusivity?
Yes, this is effective diffusion. Yes.
So I was just thinking, so there you have porosity of 1 E minus 3.
1 10 minus, yes, 1 per mil, about 1 per mil. Yes.
So you got more diffusivity close to the diffusivity in pure water.
The poor diffusion coefficient ends up being close to the fuse. Yes, that's correct. Yes. That's what comes out. Yeah. So it's like the pore diffusion coefficient. So transport distances will be equivalent. Of course, the mass transported doesn't. It's very small, but the transport distance, yeah, is similar to diffusion in both. So, yes. Right, and then these are the what we get from the model. We have three different sections across the capture going through the boreholes. So basically, we have a section perpendicular to the boreholes and two sections normal parallel to the boreholes rather. So you see, at the end of the experiment, the 3.5 years with sort of a concentration distribution that we have. So in the XY plane is relatively simple, but you have this plume, this elongated plume, going to the gallery is going down. Gallery in this system of coordinates down here. So actually we have this preferential transport going down in Z, basically to negative 6. So that's what the model is calculating. And here, that's basically we can compare it, the calculated activities in the pore water, the calculated values, and the measured values in grams per water. So what we measure is actually becquerels per gram of rock, not per gram of water. So we have to use density and porosity to transform into becquerels per gram of water and be able to compare. Actually, we have the line is a one-to-one relationship. It's not so bad, except for this. We have a few points up here that are very close to the borehole wall, but other than those points, actually, they spread around this one line. So we have a relatively good comparison between measurement and calculation. Chloride. Well, before going to chloride, I'm going to this. This is important because the measured values, they measure porosity on the samples from drill cores, and they are much higher. They are about 0.009, so close to 1%, but we get values close to 1 per mil. So what we think is happening when you drill and take the sample out, you have destressing. You don't have the confinement from the rest of the rock around it, so the rock relaxes or expands a little bit. So you have this little bit of increase. So when you measure porosity outside, even if it's still small, close to 1%, it has really opened up. So because with the measured value, it's impossible. I mean, we were going crazy. It was not possible to make any sense out of it. So we really needed to use the really small value.
I don't know so much about this kind of thing, but is a factor of 10 reasonable for?
Yeah, I mean, at Grimsel they've done that. I mean, they've done the same measurements because they impregnate with resin these pores and then this resin has this. Usually it's carbon-14, so they can make auto radiography. So basically, they can measure the porosity in the samples. They've done a similar thing, done a borehole, and then actually they've seen values down, they've measured values at Grimsel down to 0.002 or 0.0025. So not 14, but 20 or 25. So, so actually they've seen this effect, the difference between really measuring in the borehole or measuring in the samples actually you get out of the rock. So you see this, our value is even a bit lower than the measure, but you see a big reduction. Definitely you see a big reduction. Okay, so that's for tritium, and basically then based on this base case, then we did, this was the Davis master thesis, then we continued for about 6 more months, and based on this case, we did the modeling for the other traces. So starting with chloride 36, so it's basically the same domain and the same mesh as tritium. This is also a conservative trace, so it does not sorb, but being an anion, I mean, it's subject to an ion exclusion. I mean, in the granite, this is much even more evident in the clays, but even in the granite, you have the micas, we have negative charge on the surface. So if you have an anion and you have a negative surface, they don't like each other. So anions typically don't have access to the full porosity, and they also have reduced diffusion coefficient. And that's what we see. So actually, we do the same exercise, and this is a drop in concentrations, becquerels per gram of water in the injection borehole. This is the evolution in the observation borehole, and we have 2 different fits. So the ideal fit, or the one that we thought was best, was this blue line, which is a porosity of 0.0017, not 0.0, and this diffusion coefficient of 1.4 10 to the minus 12. Tritium was 3.3 10 to the minus 12. But we also forced the fit with the same value of porosity as for the tritium, 0.0014, which also it's not too bad. And then the diffusion coefficient ends up being 1.65 10 to the minus 12. So effectively, we see that we need a much smaller, factor of 2 to 3 smaller diffusion coefficient than for tritium, which is not full of water.
Do you have mineralogical evidence? I mean, do you have evidence of mica, bitite?
Yeah, it's a granite. Yeah, it's a normal granite. Yeah, sure. And then is the comparison between, as we saw, calculated values and measured values. Well, we have some spread, but I mean, actually, the dispersion is much. So in the case of tritium, say pretty happy here. Yeah, it goes around the line, but I mean, the dispersion is very big. So now, our argument, hypothesis is that we think that, yeah, of course, there is an homogeneous model, but there may be regions in the rock with even smaller porosities. So regions with even smaller porosities will have this anion exclusion effect even much more pronounced. And that's why we think we have calculated concentrations higher than concentrations in relatively large areas of the rock between, because of this heterogeneity, the combined effect of heterogeneity and anion exclusion.
So you think it's more the heterogeneity porosity is more important than the heterogeneity permeability?
I mean, the point is that the chloride does not see the full, in principle, does not have access to the full porosity. If the porosity were homogeneous, which probably is not, but tritium is neutral, is water, goes everywhere. Chloride, if you have a very small pore, cannot access that pore, basically. Okay. Because of these negative charges on the micas, basically. So that's a very important effect. There will be some heterogeneity in the permeability, for sure, but I mean, the model is homogeneous, definitely. Okay, so that's why we think it happens there. And then these are calculated, so a section perpendicular to the boreholes and a section parallel to the boreholes, and then you see this elongated tracer plume following the flow. So these are for the chloride, and now we go to the sorbing tracers. So this for sodium 22, this is weakly sorbing. Since it's sorbing, it doesn't move that much, so we need it smaller, otherwise our domain was too big, so we need to do a smaller grid. So the domain, instead of 4 meters per 4 meters in X, is only half a meter per half a meter, and discretization, the size of the element is about 6 millimeters. Same permeabilities, same porosities, same flow, basically. So this is, again, injection, goes down quite a lot because of the sorbing nature of sodium, and then observation. Then you see that the measurements are all zero, and only after about 3 years you get some value, basically. And this is the calculated. 0.1 is about detection limit, so anything below 0.1 you're not able to measure with the technique. So actually we capture the points that are above the detection limit, and we can capture them accurately. So that's it. And then the diffusion coefficient we get is about 2.2 10 to the minus 12. What for tritium was 3.3 10 to the minus 12. Similar, but a bit smaller. And then this is retardation factor, equivalently capacity factor, or equivalently the distribution coefficient. We are using linear solution. So and this is consistent with the previous experiment. So we are happy with that. And this is relatively weakly sorbing, 7.2 10 to the minus 5 cubic meters per kilogram. Then, again, as before, calculate activities in the domain and measure activities in the domain. Now it's in Becquerel per gram of rock instead of Becquerel per gram of water. So overall, I mean, they're pretty good. There are these points here that have Z measurements that may be because of issues with the measurements, could be a high detection limit for these particular samples or these particular conditions. And then something we'll see also in the strongly sorbing tracers. For some of the tracers, we see very large measurements compared to the calculated values. And then we think that we start we start to see this heterogeneity in the, in the granite we have grains, we have feldspars, we have pores and biotites, and, distributed in a certain range have a certain size, millimeters to centimeters. So actually, there will be areas where we have a little bit more biotite, or areas with a little bit less. So I think we are seeing areas probably with a little bit more biotite. So we have areas with a stronger sorption. So we see this. So with these areas with a stronger sorption, I think that that's what it means. The model is homogeneous, but the measurements actually capture whatever small scale heterogeneity is in the rock. This is clear. The granite, I mean, there's more biotite here, less biotite here, and it's not perfectly homogeneous. So this is for the sodium, and then these are the tracer profiles in parallel, perpendicular to the two boreholes. You know, the two boreholes, the transport is not very, the transport distances are short, and then if you go a section parallel to the two boreholes, you see that actually the effect of flow at this scale is very small. You don't see, for tritium and chloride, you see this very long, tracer plume, I mean, sodium, which is only weakly sorbing. I mean, does not really respond much to us. I mean, it's heavily dominated by diffusion, rather, because of the strong sorption, because everything happens in very small distance. Right. And now we go to the last two traces, cesium-134 and barium-133. These are strongly sorbing, large KD. Since they are strongly sorbing, I mean, with the 3D, it was not possible. I mean, so at the end, we ended up doing just 2D, so a section perpendicular to the borehole. However, we compared 2D and 3D we're using relatively coarse meshes just to see that we were okay. And then, using a relatively coarse mesh, we get the same results in a 2D section or in the 3D, in a full 3D domain. So we said that 2D is enough. Again, basically, you don't see the effective advection at this scale, so 2D is enough. And so the domain is 0.5 per 0.5 meters, and very fine. The size of the element is very small, 0.5 millimeters, because they move very little. So I mean, of course, this never showed up in the observation model. Was never measured in the observation, never made it there. So it's just the injection borehole, and we see the fit, so the calculated and the measurements. And interestingly, we need a diffusion coefficient, which is twice as large as the one for tritium. And this is consistent with this so-called, this is well known in the clays, the surface diffusion. I mean, the species that sorb by cation exchange, the transport parameter, the effective diffusion coefficient, is larger than water, for instance, or larger than weakly sorbing species. So that we relate that to the same mechanism. That's just a transfer parameter. Of course, that advection is huge. So KD, if it was something 10 to the minus 5 for sodium, it's 10 to the minus 3 for cesium. So actually, the apparent diffusion coefficient is very small. The transport distances are small because of the large retardation. Here's a comparison between calculated and measured values. So we have relatively good, approximately good agreement here. And then we see, as we saw in the sodium, this flat line again. This is sorbs very strongly. So when we have larger biotite content, in principle, you'll see more cesium absorbed into it. So basically, we interpret that as being caused by this, small scale heterogeneity in the mineralogical distribution. And this is the calculated tracer plume, just the injection borehole, is the observation borehole on the right. See that transport distances are of the order of centimeters or something very small. And this is finally barium, more or less the same as cesium, but it's even more strongly sorbing. So the KD is something like 1.5 10 to the minus 2 rather, cubic meter per kilogram. And we get the same diffusion coefficient as for cesium. So they're compatible. You see the strong drop in concentration given by this strong sorption in the room. And again, here the match between calculated and measured values, actually, we also see some large values up here on the right, but I mean, we have a relatively decent match between calculated and measured concentrations. And again, this is the calculated tracer flow, which is even, very narrow zone around the injection. Right, so summary of the results. So by the way, this is published this year, 2024, so the details can be found in there if you're interested. So, summary for tritium. So, we did a 3D model to reproduce the observations, both borehole concentrations and the concentrations in the rock samples. And we needed the 3D to be able to implement the effect of advection. We have this flow in a direction more or less parallel to the boreholes going into the tower. The results are consistent with previously measured values of diffusion coefficients and hydraulic conductivities. However, we needed a very small porosity. That was a big difference. So, measured porosity of rocks from rock samples from that same area is about 1%, 0.009, and we need values 0.0014. So, pointing to this unloading and distressing of the rock samples. For chloride, diffusion coefficient is about half the value for tritium. And also we have a larger, so the agreement between measured and calculated concentrations is not so good, and we attribute that to some heterogeneity in terms of, pore sizes and porosities and anion exclusion. Sodium-22 with non-sorbing, we have good results and consistent overall with previous experiment. And then, interestingly, for the two strongly sorbing traces, cesium and barium, so the diffusion coefficient is about twice as much as that for tritium. And then we have some experimental work that was done in Finland, and they did cesium sorption in the laboratory, but with very finely ground rock, so very fine grain, so with a lot of surface. So actually, the measured KVs are larger than the ones that we get in the model. But in the case of barium, we also did experiments not just with very finely crushed rock, but also with cubes, kind of centimeter, some of those kind of centimeter cubes, and some others a bit large, and then we get more or less the same values. So we have if you do experiments with a very finely ground rock, very small grain size, you have a lot of surface, so you have larger absorption. But if you do the experiment with kind of cubes, small, even centimetric size, then we have more or less the same KVs. So not all the surfaces are available in those cubes, and then it's the same situation that we get that we have in the intact rock that we model. So we have a good agreement with those measurements. I think that's also. Okay, so that was for this experiment, basically looking at transporting the unfractured rock materials. This experiment was finished and published, and now we have another experiment running since October 2022, where we really have flow along a fracture and then diffusion into stagnant zones around the fracture. Basically, this is the concept. So we have two boreholes, this is 98002 and 98004. And actually here you have some, I don't know if you can see very well, but you have some images of from downhole cameras. And these lines actually here are the maps of the small individual fracture between these portions. So in this area, this central area, this is a shear zone, so it's a highly deformed part of the granite, and this shear zone has brittle fractures, quite a high concentration of brittle fractures, and this is the part we're concentrating on. The rest is, we have packers, so the flow does not affect these parts, but we have packers separating those areas. So basically we have concentrating along this fracture, we have one injection borehole and one extraction borehole. Distance is 1.2 meters. Right. In this same dipole between these two boreholes, there was another experiment in 1999. So we're using basically the same setup. This PT1 test and use uranine and other tracers and injected an X-ray. So you have active injection and active extraction at 1 milliliter per minute. And injection of a pulse of the tracer was done during 20 hours. And then after that, you inject water, but without the tracer. So you measure the breakthrough. So since this worked well, we are using exactly the same setup.
So it's a pulse.
It's a pulse, yes. It's a tracer pulse, and then you continue just injecting Grimsel downwards. Yes. These are parameters I use for the microscopic calculations, based on results of the tritium. These are diffusion coefficients in the rock, tritium, chloride, sodium, and cesium. It's not exactly the values I just showed because this is based on previous results, but they are similar values. So it's translated into capacities, and then we have fold gouge, because these individual fractures are filled with fold gouge. Fold gouge is finely ground. It's very fine grained rock that has been, during the movement of the fold, the granite has been crushed, so we have this very fine grained porous material filling the fracture. So this is filling the fractures to some extent, so I also take this fold gouge into account. Basically, you have larger porosity in the fold gouge and larger diffusion coefficient. So for these scoping calculations, basically these are, yes. I checked two different possibilities. So you have basically, these are 2D calculations. Now you have, in one case, an homogeneous fracture meaning the whole fracture is filled with this fold gouge, so you have a porous medium inside the fracture. And basically, you have flow, it's basically one-dimensional fracture along this fracture, which is filled by fold gouge, and then diffusion into and out of the rock matrix. You just need one half of the whole system. So you take the other half. And then the other case is this consideration of a channel fracture. So basically the idea is that, well, we have fold gouge inside these fractures, but this fold gouge filling, it's probably not continuous. So you have some parts of the fracture that are open, they have no fold gouge. So we consider this the possibility of a channel that is open along the fracture. So basically you have, this would be really a 3D setup. Through some manipulation, basically you unfold it. So you have a channel, you have matrix or rock matrix, so small porosity, small diffusion on one side, and fold gouge on the other side. Basically, higher porosity, higher diffusion coefficient. So we check these two different sort of end member cases. These are parameters I already discussed, and so these are the results again. Pulse injection during 20 hours. This is the case for tritium. And you have the breakthrough curves at the extraction borehole, relative concentrations, that's linear scale and log scale. And this is the distribution of the tracer after 3 years. Basically all the numbers are, the highest number is a relative concentration of something like 10 to the minus 4. So basically, at the end you have, even if it has diffused into the rock, the tracer has auto-diffused again after 3 years. So you have the peak, so you have two curves, blue and red. Blue is the homogeneous case, so the fracture field with fold gouge, and the red is the channel case. So you have this open channel connecting the two boreholes, bounded by rock matrix on one side and fold gouge on the other side. So the curves linearly in the scale are not so different. You have a somewhat larger retardation for the channel case, because in the channel case you have the diffusion into the fold gouge, which has a high porosity, high diffusion coefficient, so you have a larger retardation. And if you look at the typical log plot that we like to use, you see this typical, the homogeneous case, you see the peak, and you have the tail with the typical slope of minus 1.5 characteristic for matrix diffusion. And you look at the channel case, it is more or less the same, and you would have a first tail which corresponds to fold gouge. So you have diffusion into the fold gouge and back diffusion from the fold gouge, which has higher porosity, high diffusion coefficient. And when you run out of that tracer in the fold gouge, then you go, concentration drops, and you see the second tail, which is from the rock matrix, which has a small porosity, small diffusion.
Sorry, maybe you have
Yes.
said that I missed.
Yeah.
Why do you have this later arrival with the channel?
Yeah, the channel one has some retardation, yes, because you have diffusion into the fold gouge, which has high porosity, high diffusion coefficient. So it's much more effective in taking tracer out of the fracture than the rock matrix, which has small porosity, small diffusion coefficient. But that's the case here. It'll get more interesting. So that's a comparison with.
But you say that this is a channel, but really this is a contact plane between the fracture and the rock. See?
These are purely 2D calculations. You can see a channel. The concept is based on a channel. These are purely 2D calculations. You can think of a plate.
I don't understand yet the channel model. It is a 2D fracture, let's say.
They are all 2D. I mean, they are all 2D. I mean, basically, the fault gouge should be in the same plane as the channel.
The 1D fracture.
Yes.
The fault core.
So you have basically the fault. I mean, this is a kind of you need some manipulation. If you imagine the fracture plane like here, you would have the channels and the fault gouge in the same plane, inside the same plane, right? But what I did is, okay, if I do that, if I unfold this, then I make it 2D. So
The channel and the fault.
yes.
Two different velocities of water velocity.
Yeah, channel is open. Yeah, channel is porosity 1, so it's an open part of the fracture. And fault gouge has a porosity, in this case, of 121. Based on
But
our
the
experiment.
flux of water is different.
Only the flux of water is only in the channel. The flux of water is only in the channel. Yes. This calculation. The flow here is through the fault gouge, but here is only through the channel, which is much more personal.
So actually you have it, but it's very similar to the matrix in the fault gouge.
It has much higher porosity, higher efficient
It
coefficient.
is different, but it is
Yes.
a sort of other matrix.
Yeah, it's a different matrix. Yeah. But I mean, but in terms of flow, here, that's important for the sorbing traces later. Flow goes through the fault gouge, here flow goes through the channel, because in principle it's the higher permeability part.
What I don't see there, that is why you use alpha there. I mean, for the left, okay, as you mentioned.
Yeah, it's all symmetry consideration.
But for the right, but maybe.
Yeah, I mean, this is not 100% correct. I mean, you have to do some manipulation, but I mean, for just scoping calculation, was easy, and then you can do very fast instead of doing a full 3D model, just 3D.
This is really similar. I mean, like the stacking is different, but it's very similar to the typical models for the river transport, where you put the hyperrake zone and then sometimes you have an extra layer.
Yeah.
So
You just put the channel in contact with different materials. And
yeah, so the order is
instead
different.
of doing it in a 3D fashion, you do it in a 2D fashion.
Yeah, but the river thing is very similar. So you can, I think you can calculate a lot of this analytical, at least the tails you should be able to get from it.
Yeah, again, the point here was just to see what we can expect from the results, rather than to make a really accurate calculation. In any case, we compared with the result experiment in 1999 with the same conditions, and actually the measurement is this second red curve that you see. You'll see a red curve that's a bit shorter than this one. So this is what the measurement was in that experiment. So well, we are in that general region. Again, this is just to see what we can expect from the experiment, not to make an accurate calculation. So okay, so we are capturing more or less general behavior. That's good enough. I mean, that was the idea. So that was for 3D. Okay, so that's for chloride. So same story. And chloride behaves quite similar. So again, we have here is a linear scale, here log scale. So we have homogeneous, the first arrival and the peak are a bit earlier than the channel. And again, it's the same region, because you have in the channel case, we have diffusion into the fault gouge. And you see the two tails in the channel case, the only one tail
In the data, the tail is way fatter, right?
Again, sorry?
The tail in the data was way heavier, or did I misread?
I mean, this is for tritium. Yeah. I mean, this is.
It's a super heavy tail.
This is, of course, reality is not quite as simple as that model. The point was not to replicate, was not to model this experiment, but to have an idea what we can expect, because we are also using other traces at the end.
So this was a blind prediction. So you did.
It was not even a prediction. Yeah. I mean, I just wanted to check if it's at least comparable to some extent. I mean, it was just to see, to help in the design of the experiment and what can we expect. It was not really trying to model the experiment per se. Because I'll show some results. Yeah. Okay, this is for sodium. Then things start getting interesting. Sodium, because you have this weakly sorbing tracer, and then again you see the homogeneous case. And then the channel case, and now you see the channel case, the breakthrough is a bit earlier actually than later. Right? So before, the red curve comes later than the blue curve. And now for the sodium, it's the other way around. That's because it's getting interesting. What happens in the homogeneous case, flow is through the fault gouge. So flow is through the area where sodium soaks onto the mineral. So you have retardation directly in the flowing zone. So that's why, while in the channel case, to have sorption, you have to diffuse either to the fault gouge or the rock matrix, but the channel is porosity 1, there's nothing in there. So that's why you have this reverse in the arrival. But that's weakly sorbing. But the really interesting case is when you do a strongly sorbing case. I mean, listen, if you have the channel case, you have very quick arrival, so the same basically as the residence time of water. And the homogeneous case, the breakthrough is much later. Yeah, that's again the same reason. The homogeneous case flows through the fault gouge, so you are sorbing actively in the fault gouge. In the channel case, you have to diffuse to the fault gouge and then sorb. So actually our concept of the experiment, to part of the experiment is based on that. I mean, if the system is channel or homogeneous, there would be a big difference in the breakthrough of the strongly sorbing traces. Not so much for the weakly sorbing or conservative, but for the strongly sorbing traces, it should be completely different. You should either see very early arrival or very late arrival. Depending on very early arrival, if the system is strongly channeled, very late arrival if the system is more homogeneous. And then, on top of that, then also thought, well, you can do it even a longer pulse. So instead of 20 hours, it is a 21-day pulse. Again, decision. Then, of course, the peaks are getting higher, but you still see this difference, basically. Early breakthrough for the channel system, but late breakthrough for the homogeneous system. The difference is that if we have a longer injection period, basically, the difference, this number was much smaller in the other case. We are putting much more tracers soaked into the rock, so we want to take advantage of that. Inject for a long time, and then be able to see that tracer soaked into the rock. Rather than looking at the tails of the breakthrough curves, we want to look at the tracer which is soaked into the rock. So based on this, the concept for the experiment, this is the concept now of the experiment. So we have what we do in the two boreholes, the injection borehole and the extraction borehole. So then we did that. We've already done this part. So first we inject water, you make sure you have a steady state flow regime. Then we do the 20-hour pulse, which was actually tritium, sodium-22, and uranine iodine. So that's that you can measure. The point with the uranine is that you can measure in situ. The tritium and the sodium-22, you have to take samples and take to the lab. But the uranine you can measure in situ. So 20 hours and then inject for a long time, just Grimsel water and look at the tails. I'll show you later. And then sometime later, we haven't done that yet, inject the poles with the strongly sorbing tracers. And the idea is to stop right after, inject the tracers. And then overcore. So what to do is you want to look at the tracers soaked in the rock actually. Rather than the tails, look at the tracers soaked in the rock. Because then you will be able to see where it soaks, how it looks like, how it is related to the structure of the rock. Be able to see the structure of the flow field in a way. And then you do the different sampling frequencies depending on the part of your interest. But basically, that's the strategies for the first part, which already did. We do the pulse, which is very short, and then we should inject water for a long time, and we want to look at the tails of those breakthrough curves and try to interpret that. That's already doing that, and I'll show you the results. And the second part, it has not started. Should have started 23, 24, happened later this year. So we'll do that. Inject the strongly sorbing tracers, 21-day pulse. While we are injecting, we're also measuring at the extraction borehole. So if there is an early breakthrough, we'll see it. If we don't see it, then we'll know that the system is homogeneous. But if we see it, we'll see that there's an effect of channeling also strong. But then it is the overcore, so take rock samples and look at those. Where does the activity go? Where water has flowed, basically, at the end. And these are the results that we have. I covered the numbers because even some people in the project haven't seen that yet. So well, maybe I'm not showing the numbers, but the numbers are not really so important. But you see the different. So in blue you have the tritium. In orange you have the sodium-22, and this is the uranine. The gray symbols is the uranine. The uranine, the advantage again is that you measure in situ. So So in real time, you see how the system is evolving, and then it's good that we have a very good match between tritium and uranine. They are both conservative, and then after some time, I think uranine, I mean the detectability is not so good. Lower concentration, then you have problems. So eventually they diverge. We can capture the peak very nicely and the relative concentrations very nicely. So that was good, but there's interesting differences between the tritium and the sodium. Well, clearly you have this lower peak, which is clearly due to sorption, sodium sorbs.
What is the, oh, sorry.
Not sure.
Just going to ask what the telling exponent was for the blue curve for you.
Sorry, that?
What's the telling exponent that you get?
The tail.
Yeah, is it 3 halves?
Yes. Interesting.
Okay, so yeah.
For the tritium, you get this slope of -2, which is characteristic. I mean, in some papers, you see these kind of values are typical of these heterogeneous advections. So you have contributions from different fractures and or channels inside fractures with different permeabilities, different flow rates. And since they overlap, they end up giving this value of alt -2. But the interesting thing is that for sodium, then you get the -1.5. I mean, beautiful. So it's quite interesting. So that's so
what is the difference between them? Because
sodium sorbs.
Okay.
Tritium is conservative, but not sorb. Sodium does sorb.
so that's
Not strongly, but sorbs. Yes. So that's a difference. That's a difference. But I mean, I've never seen that. I mean, this sort of difference, and well, we want to explore that. These results are very, very recent, fresh from the lab, basically. So that
Super cool. Like,
no, the data are very good. The data are really nice. I
the
mean,
max is surprisingly thin. It's a bit, I mean, you didn't put the numbers, but still, it looks like a,
yeah, no. I mean, these are.
looks like a big range of.
Yeah. I mean, these are well done experiment. Definitely. I mean, there's no doubt.
I'm surprised that it's so clean, the -2, especially.
Yeah. No, I mean, since I put them, so here I can really, since when I have the numbers, I can really get the exact slope, and then you just move it, and that's the numbers I get. So that's what we have, and then the idea is now we have to model this. So basically, this is the next steps, which is my last slide. So basically, so we have to develop a concept which will involve definitely different fractures and or channels within this fracture plane, and we'll model this and see we can reproduce these breakthrough curves, and we can explain this difference between the tritium, so the conservative tracer, and the sorbing tracer, these different slopes. So this will be a first part, and then after we have the second pulse injection with the strongly sorbing tracers, then when we have the analysis, then we'll have an idea of really what's the real flow field. We'll have an idea where does water really flow, and then use that to basically do a final modeling. So first we will do just not even a simple model, maybe just using different combinations of 1D or 2D fractures, and you can add them up and see if you can end up getting the right breakthrough curve. But at the end, we'll have in principle a better idea of how does the flow field look like, and then do a final model after we have the work. So that's more or less the plan for the future. And yeah, that's Grimsel in winter.
Okay, so no questions?
No.
There were already.
You already quite a few questions.
About these breakthrough curves, I know that you can show the numbers, but how much mass did you recover?
It's about, for tritium, it's about 90-something%, and sodium, I'm not sure right now, I don't remember now. I think it's similar. They are hard. I mean, in that GAM, that old experiment, recovery was 100%, even larger, I say. I guess, the details of how we calculate recovery may be important, but I think in that table at the beginning, or maybe not too far. Oh, it's not. It's in another table. But I think they say 104%. But anyway, it's complete recovery. And so far for tritium calculated, it's 90-something%. Sodium, I don't remember exactly, but I think it's quite high. Maybe it's 80-something%. I don't know. But tritium was basically complete. Yeah, very good. I mean, you're injecting 1 milliliter per meter. We are extracting 1 milliliter per minute. So kind of force the flow to go to where you want, but, yeah.
Just another question about, well, if you can reveal a little bit more of the secret. How many orders of magnitude are there in this?
Well, we injected during, we know, I mean, consider the dates. I mean, this is lasted, I mean, basically, when we started injecting in 2010. Sorry. Let me go. Here, we started injecting October 2022, so it's about 1.5 years now. So, yeah, the tech scale is of the order of a year or something like that. It's something like a year.
Yeah, but this is a lot.
Yeah,
So
yeah.
At the left you have 1 day, and at the right you have a year or something.
Yeah,
Okay.
yeah. It's a spans to 2 or 3 or 4 units in logarithmic scale. Yeah.
At the end of the questions, you'll be able to put all the numbers.
No, I'm not showing. I mean, I didn't want to show it to the camera. I can show you. I didn't want to bring on record, but I can show you. No problem.
I think we can already deduce it.
Yeah, I think you can work it out. I mean, I can work it out.
When the tests are so clean, it's clear that there's a...
You can. I'll show you. I'll show you the number. No problem. I just didn't want to.
I did want to ask you one thing. So in the first experiment,
Yes.
when you look at the observation boreholes, I think in all cases, you have this crazy overshoot. Is that
Yeah.
a real thing, or do you know?
Yeah, I think that's real. I mean, if you look at the treaty.
And that is sort of awesome.
Yeah, this. I mean, this. Yeah, because I mean, this you have advection. So basically, you have a peak that comes with the flow of water, and of course, at the same time, the concentration in the injection borehole is going down. So actually, you take more concentration at the beginning and less concentration at the end. So actually, the model does that as well. It goes up and goes down.
But this guy, like, it goes up like crazy. But then
That is we don't capture that. That small details. We don't.
But it's real. You think it's real?
It's real, but it may be an artifact of a sampling procedure. It may be an artifact.
Then you have this point.
Because then it goes down, and it's...
But it goes down. It's consistent with the model. That it goes down.
No. It goes down like crazy.
Oh, here, no, it goes, yeah. So
No.
it goes like this, and then goes like this, and then goes like
Yes,
this.
that.
Yeah.
That's what...
Then maybe issues with sampling and I mean, yeah.
But it's there in all the curves, isn't it? Like,
Can be an error of the sample.
it is there in all the curves, though, right? Like all the experiments have this.
No.
Okay.
In other, let's see, you can check.
Yeah, like that's even more.
Goes up and goes down.
Yeah. So I wonder if that's a real thing because if
Could be. Yeah.
it's hard to
And then of course sodium, you don't get anything until the end. And the other two, they never.
but this is detection limit.
Again, the model is very simple. Completely homogeneous model, and constant steady state flow, and everything very simple. And the idea was, well, with this concept, we can explain the results. Of course, the fine details. I mean,
It was not a criticism. It's just like I've never seen.
No.
that kind of behavior.
No. I mean, absolutely. Right.
If it's a real thing.
That's the number that they measured. I mean, at the end. But I mean, I think that's more. I think that the analytical error is much smaller than that. I think the analytical error is the order of 10% or almost 20%, and this is more than that. I mean, I think this has to do with sampling or maybe some perturbation of the system or some other. I mean, the injection was always very nice, and the observation was kind of. Yeah. Maybe also the effects of heterogeneity impact more this part of the plot than this part.
Preferential thing.
Because this is just a first arrival, and you still have small concentrations, and maybe it's more sensitive to this heterogeneity injection.
I have a comment about the porosity value. So you mentioned that
Yes.
the theory is that you have this difference in porosity because when you take the sample out
Yes.
of the confinement,
Yes.
then you have an expansion. That's true. But it's also true that granite is very stiff.
Yeah, no, but I mean, again, with this.
Grimsel is not very deep, right?
No, it's I mean, you have about 300 meters overboard.
So it's like, I mean, the confinement is not very big, the rock is very stiff,
So you can even test that if then in the lab you reconstruct the same confinement, you apply this confinement and you see the formation of the sample. I kind of don't believe that you can have it 100%.
But the one thing they've measured, I mean, there's a paper about that I can give you, that they've measured this, they've done this, because they use this resin impregnation technique to measure the porosity. They've done the same in a borehole.
Yeah, but my question is, I think this is much more an effect of heterogeneity, that you sample somewhere and then you look at the porosity overall, and so you have some differences because in the end the sample is a tiny part of the reservoir compared to the rest. I think this heterogeneity plays a much more important role because this is very significant.
But,
Porosity, an order of magnitude, but that's crazy.
I mean, you can have in your sample, maybe you have a crack or something that gives you all the porosity.
I mean, no, I mean, this can visualize, I mean, the way they measure this, I mean, they do this auto radiography, and they see that, I mean, they see the sample, they visualize. I mean, they are sure that it's not caused by some strange particularity of the structure in that case.
The point is that 300 meters is like 3 megapascal, and then the stiffness is order of gigapascal for this rock. So
I think there is some calculation in Fresky done for S from the stress effect of stress release on porosity. Now, I don't remember the numbers, but there is some.
No, but again, I mean, numbers that measure in the laboratory different areas and around this. Closer to 1%, so 0.06%, 0.09%, 0.04%. These are the sort of numbers that you see in different samples. And this number has never been measured in any sample. I mean, I've seen samples with 0.04, I have seen 0.06, I have seen 0.09, I have not seen 0.01.
Is it very low?
But this has been seen. But this has been seen in the borehole. In the impregnation in the borehole, then they've seen 0.002. They've seen 0.002 or 0.025, I don't remember exactly. But I mean, a number very close to this.
I don't know how they made the measurement in Naga, in the Grimsel, in the Tebex zone, the same Grimsel site, it was 0.003 in the matrix. That is the value of this. The same place on tunnels on the right.
But this is really the matrix. I mean, it's very pure, almost.
Yeah, it is. Yeah. No, the point, I mean, I will not defend that it's 0.004, but it's a small, it's smaller than what you measure in the lab.
But it is like an order of magnitude.
It could be close, yeah, because the value measured was 0.009, so yeah, it's getting close to. So maybe a factor of.
What measures of water separation?
This is what they measure in the laboratory. They do auto radiography. Auto radiography. Yeah. So basically, with this impregnation of a resin that's doped with a radioactive tracer, and kind of radiography of that, and you digitalize that image. I mean, I've seen different values in different areas of Grimsel, but again, I've seen 0.004, I've seen 0.0065, I've seen 0.00. From these experiments, samples from this experiment, they measure 0.009. And we are there, I mean, so closer to 1% than to 1 per million. This value is closer to 1 per million than to 1%. I'm sure, so I think we see this effect. Maybe it's not exactly that number. That's a little bit, comes from the model, so maybe it's a bit larger than that. But it's, I think it's, for me, there's no doubt that you get some effect like this. So what you measure is always a bit larger than what you have in the intact row.
I just have a final, probably stupid question. I didn't get it. In the slide where you show the various slides where you show measurements versus calculated activities.
Yeah.
This one, for example, especially the ones where it flattens out. That was more.
Yeah.
But anyway, I guess the question is general. Like, what is the data for this? Like, what is the relationship between this and the previous slide, for example?
This and this. Yeah. Well, the relationship basically is these values. Yeah. These high calculated values. Basically, why is this flat? Because this corresponds to this. So basically, at the end of the experiment, this is the last concentration in your borehole. So basically, all the points just around the borehole have this value. But
I don't know, maybe.
I think the question also is,
No, what is this?
this is just in the borehole.
this is the water in the borehole.
What the concentration, and the other one is at the end of the experiment.
Yeah, that's the question. What is it?
This is at the end of the experiment, yeah. That's rock samples. These are rock samples.
Okay.
These are rock samples. They are at the end of the experiment, you stop and then you go with these other boreholes. And then you take rock samples. So these are measurements in the rock. They are measurements in the rock. So at the end of the experiment, at a given time.
Because this looked, I mean, those values there, they look much worse than what I was seeing in the plot. The plot looks really
Yeah,
This
is both. This is this is concentration versus time in the injection borehole, in the observation, extraction borehole rather.
Yeah, and then you have
And these are concentrations calculated or measured at the end of the experiment in the rock. Yeah.
Sorry, I didn't.
Yeah,
I got it.
Yeah.
That's why there's way more points than it was. That makes sense.
Yeah. And even, when you put them together, there's a few, but actually, I mean, if you put all the samples in the 3D, I mean, it's not that many points.
No,
because it's difficult to get so many samples.
No, I get it.
Okay.
Lively discussion.
No, it's good. Yeah, no, it's great.
¿Equipo de modelizadores ahí también, como en las fotos? ¿Hay varios modelizadores?
En teoría sí, en realidad esto lo he hecho yo. Bueno, nosotros, yo no. Lo he hecho Debbie, básicamente, pero vamos, nosotros, Lourdes, Rafael, Debbie.
Ah, no es que cada organización tiene su equipo, ¿no?
Han hecho, pero no han hecho, digamos, no le pusieron todo el esfuerzo. En Japón también hicieron, en la República Checa también hicieron algo, pero nunca terminaron de hacerlo. Sí.
Tú trabajas por Mac.
Sí. Dios me paga. Poco, pero me paga.
Muy bien.
Sí, ¿no?
¿Quieres que hablamos?
Vale, sí.
Hasta luego.
Venga, chao.
La tenés que parar de grabar.
Ah, sí.
Escribiste